Hi everyone, welcome to my practical machine learning F1 presentation on abalone age prediction. Predicting rings from easily measured features. The age is rings plus 1.5. Multiple linear regression and ridge tie on core metrics. R square is 0.53, MSE is 5.10. But Rich shows a heavier worst-case tail. It's about 210% relative error. I select MRR as the best overall baseline. MRP and KN slightly improve MAE, but have lower R square. The feature here is sex, length, diameter, height, and whole shaft or viscera or shell weight. The target is rings. Age is rings plus 1.5. UCI dataset with 4,177 samples and 8 features. This is a basic background of this dataset. Here is the libraries. This is what we should do to make preparation before running the code. Using a scikit-learn, UCML repo for data batch. So let's go into the data. We can get the data from this website. Here is importing the data, and this is the overview of the data. Here is the shape of the data. We can know that. Then let's go into the EDA part. Here shows the dataset shape, and just like what I mentioned before. And the data is very clean. There's no duplicates. There's no missing values. So the data is very clean and perfect. Okay, let's move on to the auto visualization outputs. What does AutoVista do? It auto generates EDA with DFTE is DF like this here. Okay, let's move on to the result of that. Here is the data quality table. No missing values, but many outliers across length, diameter, height, whole-shaped visceral share weight. Race has many too. Strongly collinearity flags, like diameter, length, or whole weight with length or diameter, just like there's several on here. Is a pairwise scatter matrix. Length diameter nearly linear. Size versus weight rise with curvature. Shaft weight very tight. Shell weight relates strongly to whole weight. Height shows weaker association and extremes. Nonlinearity is present. Manage collinearity. Next is here is scatter plot of all continuous variables. It's very near linear. See, and let's go to the unvariate triplets like histogram, foxtrot, and cuckoo. Length and length and diameter mildly left skewed. Skew is about minus 0.6. Weight right skewed. Weight is right skewed. It's about 0.5 to 0.7. Height. Height. Height highly right skewed is more than 5, with many high and obvious. Consider scaling, reversed methods, and possible transforms. Normalized distributions of sex in rings. Sex fairly balanced. Rings peaks around 8 to 11 with long tails. Older age reveal, suggesting CVO stratification. And here is a violent thought. It visualizes central mass and tails. Highest upper tails is long to long. Weight right skewed. Length and diameter tighter. Consistent with his old box of video. Let's go into the correlation heat map. Length to diameter is about 0.99. Her weight to shift weight is about 0.97. Her weight to shear weight is about 0.95. Many pairs more than and equal to 0.9 is a very strong multicollinearity. Correlations with rings. Shear weight is about 0.62. Diameter is about 0.57. Length is about 0.55. Height is about 0.53. Height is about 0.51. Visceral weight is about 0.5. Shock weight is about 0.41. Linear signals exist, but is incomplete. Here is a bar plot. Continuous by sex and by race. By sex means often older and more than a male, more than female, more than infants. Infants are smaller. Encoding captures this. The range. Continuous rings increase roughly monotonically with rings matching biology. Regression on rings is sensible. Here shows the scoop of the quant like Nicholas lens. Here it is. it's the skewness. Then we move on to the use Tukey rule of the useful target price in opening. Here is the box plot to check outliers. Let's move on to the feature importance. Here is the random forest regressor bar chart. It ensembles reduced variance and provides stable importance, highlighting which size of the weight features matter most. So here the share weight counts most is the most important one. And next is chef weight. Let's move on to the base linear regressor after the Coda sample. The common metrics we know that is MSE, MAE, and R square. It's under same preprocessing and holdout. And we know if the R square bigger, it's better. Okay, let's see the results. This is the multiple linear regression. It has the R square is 0.53. Here is the detailed information. And this is the picture of the relationship between actuals and predictions. It shows that the maximum error is about 81%. Okay, the next one is the lossy regression. It's not so good because the R square is very low, like 0.14. Okay, the error is so big. And then we're going to the ridge regression. Okay, also the best one. Its R square is about 0.53. Okay, the error is similar to MAR. This one is elastic net regression. And it's performed not so good, but not so bad. This one is KNN regressor. The R square is big, but not the biggest one. It also performs good and its error is low. It's about 80%. This regressor is called SVR. And also it's not so good, but okay. This one is decision tree regressor. The R square is 0.21. It's low. Next one is regressor called multilayer perception. It's good. It performs good, but not the best one. So considering core metrics and tail risk, I select MRR as the best baseline. So next step is add K for CV and tuning in training, extend comparison to random forest, gradient boosting, and XG boost. So much for this presentation and thank you.